last video on improper integrals for us, and it has to do with the comparison test. All right, so we need a little supposition first. So suppose that you have two continuous functions. So f and g are continuous. With, let's see, we're going to make them positive valued. So f, we're going to say, is bigger than g, both of which are bigger than 0. And we'll say for x greater than a. We don't care what happens to the left of a. All right, a couple of things. If you have the integral from a to infinity of f of x dx, so the one that sits above g, if this is convergent, and we know what convergent means of an improper integral, if it's convergent, then the one that sits underneath, right, as long as it's positive valued, is also convergent, right? G of x dx is also convergent. Right, so one way to think about that, let's say we had f, and we're saying that from a on, this sum of the area under this curve is converging to a value, and we had another function that was underneath it. Oops, I wanted to change that color, and I did not. So here the green is f, and the pink is g. Well, then what's underneath has to have less area than the what's above it if they're both positive valued. So it has to also converge. So that's one thing it says. Now, notice that if f, the one that sits above, diverges, then I can say nothing about g, right? G could diverge or converge if it's underneath something that blows up, right? I don't know what it does. But what I can say is if the one that's underneath, so if a to infinity of g of x dx is divergent, so it doesn't go to a nice number, it blows up to infinity, then the one that's above it has to also do the same, right? It can't converge to a number and then something that has positive area underneath goes to infinity. So then this integral is also divergent. Now notice, if the one underneath, all we know is that it converges, the one above it could do either. So we know nothing. All right, so let's see why this might be of use to us. So if I asked you, is this integral from 1 to t of e to the negative x, sorry, I don't want to say t, I want to say infinity, dx, is this convergent or divergent? Well, we would do what we've been doing, right? So we would say, okay, well, let's consider the limit as t goes to infinity of 1 to t of e to the negative x squared dx, right? Same as before. We would then say, okay, we have to first evaluate this definite integral. The problem is we can't. This thing right here does not have a closed form antiderivative. We don't know how to do this and won't know how to do this until we develop to actually evaluate this Taylor series. Okay? So this is a great candidate for comparison. Like maybe we can bound it between things that we know that do something. All right? So my first claim to you is that this integral, consider this integral. I'm going to walk it through 1 to infinity of e to the negative x dx. And through your work, you can show this converges. Okay? Now, my next claim is that e to the negative x squared is smaller than or equal to e to the negative x. Right? Because if we're, this x squared will get bigger and bigger and bigger, so the negative of a bigger number is smaller than the negative of a smaller number, right? So, by the comparison test, this guy, 1 to infinity of e to the negative x squared dx, converges. That's it.